You've probably heard a million times that AI can see, that it can pick a cat out of a photo, no problem. But have you ever really stopped and wondered how it goes from just knowing what's in the picture to knowing exactly where it is? That's the fascinating puzzle we're going to tackle right now. Okay, let's really break this down. On the left, you've got a task called classification. The AI looks at the whole picture and just spits out one label, cat. Pretty straightforward. But on the right, that's object detection, and that is a whole different ballgame. The AI doesn't just need to know a cat is there, it has to draw a box around it, maybe around a couple of dogs too. So how in the world does it make that leap? Right, so to get how that works, we really have to peek under the hood and see the different ways a computer can be taught to look at an image. And trust me, it goes way beyond just a single, simple label. And this table just lays it all out perfectly. You start with classification, that one simple tag. Then you level up to object detection, where you're drawing boxes around things. But then you get to semantic segmentation, which is kind of wild. It colors in every single pixel. Is it grass? Is it sky? It knows. And the final boss is instance segmentation, where it not only colors everything in, but also knows that this dog is not that dog. Okay, but here's where things get kind of weird. A real paradox, actually. The very thing that makes these neural networks so good at figuring out what something is, well, it completely destroys the information about where it is. Let's dig into that. So just look at this. This is a classic neural network. You see how it takes this big, detailed image on the left, and then layer by layer, it shrinks it down? It's literally like a funnel, squeezing all that rich visual info into this tiny, dense little package of numbers on the right. For just telling you there's a cat in the photo, this is perfect. And this is the absolute key. In that whole process of shrinking and summarizing, we're basically throwing away the where. The network can confidently say, yep, that's a cat. But it has completely lost the map. It has no idea where in the image that cat was. So how do we get that map back? Well, the answer is this really clever trick called upsampling. It's almost like we're teaching the network to work backward to rebuild the very spatial map that it was designed to throw away in the first place. And yeah, this really is the million-dollar question, right? The whole point of the network was to trade fine detail for a big picture understanding. So how can we possibly go in reverse and get that detail back when we need it? And the answer, believe it or not, is upsampling. Honestly, the best way to think of it is like a smart unpixelate button from a sci-fi movie. You know that small compressed blob of data the network made? Upsampling takes that and intelligently blows it back up, trying to recover all that location data it lost. Okay, so how does this whole unpixelating thing actually work? Let's get into the nitty-gritty, and you'll see it's surprisingly simple. It all comes down to numbers. Forget about complex images for a second. Just imagine the network has crunched some information down into this super simple 2x2 grid of numbers. A 1, a 2, a 3, and a 4. Our job is to make this little grid bigger. So there are a couple of common ways to do this. You've got the simple way, called nearest neighbor, and then you have a smarter way called bilinear interpolation that gives you a much nicer looking result. All right, check this out. This is nearest neighbor in action. To make our little 2x2 grid of 4x4, we just copy and paste. The 1 becomes a block of 4 ones, the 2 becomes a block of 2s. You get the idea. Super simple, right? But you can see the downside. You get that blocky kind of jagged look, just like a bad digital zoom. Okay, now for the smarter way. Bilinear interpolation. Instead of just copying, it gets creative. It actually calculates new numbers to fill in the gaps by looking at its neighbors and blending them. See those numbers like 1.25 and 1.75? They weren't there before. The algorithm created them to make a smooth transition. And boom, here's the payoff. On the left, that's what happens when you just scale up the pixels, a blocky mess. But on the right, using interpolation, you get a much smoother, much more natural image. We've basically unpixelated the AI's internal idea of a dog. I mean, the difference is just night and day, right? Okay, so we've got the basic idea of upsampling down. Now let's put it all together and see how this one technique is the secret sauce that powers a real-world object detector that you may have heard of, called YOLO. So this table here, it really nails the key difference. A normal network, like Darknet, is built to give you one single answer. But look at YOLOv2 Tiny. Its whole purpose is to output a region, basically a grid or a map full of potential answers. And at the very end of this whole process, for every single spot on its final grid, the YOLO network spits out 425 channels of information. And I know what you're thinking, 425? Where did that number come from? It seems totally random. But it's not. Well, it's not random at all. That 425 is an incredibly organized packet of information. Here's how it works. For each little spot on its map, the network guesses 5 different boxes. For each of those boxes, it gives us 85 pieces of data. 4 numbers for the coordinates, 1 number for how confident it is that anything is in that box, and then 80 numbers for how likely it is to be one of 80 different objects. So what do you get when you multiply 5 boxes by 85 values? You got it, 425, our magic number. And that, right there, is the big aha moment. The network does all that crazy shrinking, right? But then at the very end, it creates this small, efficient 13 by 13 treasure map. And each of the little squares on that map is packed with all the clues it needs to go back to the original big picture and draw the boxes in exactly the right place. And you don't have to take my word for it. This quote from the research paper itself just says it all. The end of the network is built for one thing, outputting everything you need for object detection: the boxes, the class predictions, and the confidence scores. So think about the journey we just took. We went from a simple single label, cat, to this incredibly detailed treasure map that lets an AI find things with amazing accuracy. It learns to throw away detail to understand the big picture and then cleverly rebuilds just enough of a map to find what it's looking for. Which leaves us with a really big question. What's next? If an AI can find things, what's it going to take for it to actually understand a scene, the relationships, the context, the story? That, my friends, is the next great frontier.